Hello and welcome to our YouTube channel Know How. Today our topic is Milky Way Galaxy. We will discuss its size, definition and some facts about the Milky Way Galaxy. So let us start our topic. Milky Way Galaxy. The large spiral system consisting of several hundred billion stars, one of which is the Sun. It takes its name from the Milky Way, the irregular luminous band of stars and gas clouds that stretches across the sky as seen from Earth. Although Earth lies well within the Milky Way galaxy, sometimes simply called the galaxy, astronomers don't have as complete an understanding of its nature as they do of some external star systems. A thick layer of interstellar dust obscures much of the galaxy from scrutiny by optical telescopes, and astronomers can determine its large-scale structure only with the aid of radio and infrared telescopes, which can detect the forms of radiation that penetrate the obscuring matter. Let's now discuss major components of the galaxy: star clusters and stellar associations. Although most stars in the galaxy exist either as single stars like the Sun or as double stars, there are many conspicuous groups and clusters of stars that contain tens to thousands of members. These objects can be subdivided into three types: globular clusters, open clusters, and stellar associations. They differ primarily in age and in the number of member stars. Let's discuss them one by one. First, globular clusters. The largest and most massive star clusters are the globular clusters, so called because of their roughly spherical appearance. The galaxy contains more than 150 globular clusters. The exact number is uncertain because of obscuration by dust in the Milky Way band, which probably prevents some globular clusters from being seen. They are arranged in a nearly spherical halo around the Milky Way, with relatively few toward the galactic plane but a heavy concentration toward the center. The radial distribution, when plotted as a function of distance from the galactic center, fits a mathematical expression of a form identical to the one describing the star distribution in elliptical galaxies. Globular clusters are extremely luminous objects. Their mean luminosity is the equivalent of approximately 25,000 suns. The most luminous are 50 times brighter. The masses of globular clusters measured by determining the dispersion in the velocities of individual stars range from a few thousand to more than 10 lakh solar masses. The clusters are very large, with diameters varying from 10 to as much as 300 light years. Most globular clusters are highly concentrated at their centers, having stellar distributions that resemble isothermal gas spheres with a cutoff that corresponds to the tidal effects of the galaxy. A precise model of star distribution within a cluster can be derived from stellar dynamics, which takes into account the kinds of orbits that stars have in the cluster, encounters between these member stars, and the effects of exterior influences. The American astronomer Ivan R. King, for instance, derived dynamical models that fit observed stellar distributions very closely. He finds that a cluster's structure can be described in terms of two numbers. One, the core radius, which measures the degree of concentration at the center, and second, the tidal radius, which measures the cutoff of star densities at the edge of the clusters. A key distinguishing feature of globular clusters in the galaxy is their uniformly old age, determined by comparing the stellar population of globular clusters with stellar evolutionary models. The ages of all those so far measured range from 11 billion to 13 billion years. They are the oldest objects in the galaxy and so must have been among the first formed. That this was the case is also indicated by the fact that the globular clusters tend to have much smaller amounts of heavy elements than do the stars in the plane of galaxy. Example is the Sun, composed of stars belonging to the extreme population, as well as the high latitude halo stars. These nearly spherical assemblages apparently formed before the material of the galaxy flattened into the present thin disk. As their component stars evolved, they gave up some of their gas to interstellar space. This gas was enriched in the heavy elements, like example elements heavier than helium, produced in stars during the later stages of their evolution, so that the interstellar gas in the galaxy is continually being changed. Hydrogen and helium have always been the major constituents, but heavy elements have gradually grown in importance. The present interstellar gas contains elements heavier than helium at a level of about 2% by mass, while the globular clusters contain as little as 0.02% of these same elements. Now let's discuss second type, open clusters. clusters smaller and less massive than the globular clusters are found in the plane of the galaxy, intermixed with the majority of the system's stars, including the Sun. These objects are the open clusters, so called because they generally have a more open, loose appearance than typical globular clusters. Open clusters are distributed in the galaxy very similarly to young stars. They are highly concentrated along the plane of galaxy and slowly decrease in number outward from its center. The large-scale distribution of these clusters can't be learned directly because their existence in the Milky Way plane means that dust obscures those that are more than a few thousand light years from the Sun. By analogy with open clusters in external galaxies similar to the galaxy, it is surmised that they follow the general distribution of integrated light in the galaxy, except that there are probably fewer of them in the central areas. There are some evidence that the younger open clusters are more densely concentrated in the galaxy's spiral arms, at least in the neighborhood of the Sun, where these arms can be discerned. The brightest open clusters are considerably fainter than the brightest globular clusters. The peak absolute luminosity appears to be about 5,000 times the luminosity of the Sun, but the largest percentage of known open clusters has a brightness equivalent to 500 solar luminosities. Masses can be determined from the dispersion in the measured velocities of individual stellar members of clusters. Most open clusters have small masses on the order of 50 solar masses. Their total populations of stars are small, ranging from tens to a few thousand. Open clusters have diameters of only 2 or 3 to about 20 light years, with the majority being less than 5 light years across. In structure, they look very different from globular clusters, though they can be understood in terms of similar dynamical models. The most important structural difference is their small total mass and relative looseness, which result from their comparatively large core radii. These two features have disastrous consequences as far as their ultimate fate is concerned, because open clusters are not sufficiently gravitationally bound to be able to withstand the disruptive tidal effects in the galaxy. Judging from the sample of open clusters within 3,000 light years of the Sun, only half of them can withstand such tidal forces for more than 200 million years, and a mere 2% have life expectancies as high as 1 billion years. Mirrored edges of open clusters agree with the conclusions that have been reached about their life expectancies. They tend to be young objects. Only a few are known to exceed 1 billion years in age. Most are younger than 200 million years, and some are 1 or 2 million years old. Ages of open clusters are determined by comparing their stellar membership with theoretical models of stellar evolution. Because all the stars in a cluster have very nearly the same age and chemical composition. The differences between the member stars are entirely the result of their different masses. As time progresses after the formation of a cluster, the massive stars which evolve the fastest gradually disappear from the cluster, becoming white dwarf stars or other under-luminous stellar remnants. Theoretical models of clusters show how this effect changes the stellar content with time, and direct comparisons with real clusters give reliable ages for them. To make this comparison, astronomers use a diagram, the color, the color magnitude diagram, that plots the temperatures of the stars against their luminosities. Color magnitude diagrams have been obtained for more than 1,000 open clusters, and ages are thus known for this large sample. Because open clusters are mostly young objects, they have chemical compositions that correspond to the enriched environment from which they formed. Most of them are like the Sun in their abundance of the heavy elements, and some are even richer. For instance, the Hyades, which compose one of the nearest clusters, have almost twice the abundance of heavy elements as the Sun. It became possible in the 1990s to discover very young open clusters that previously had been entirely hidden in the deep dusty regions. Using infrared array detectors, astronomers found that many molecular clouds contained very young groups of stars that had just formed and in some cases were still forming. Now let's discuss third type, stellar associations. Even younger than open clusters, stellar associations are very loose groupings of young stars that share a common place and time of origin, but that are not generally tied closely enough together gravitationally to form a stable cluster. Stellar associations are limited strictly to the plane of the galaxy and appear only in regions of the system where star formation is occurring, notably in the spiral arms. They are very luminous objects, the brightest are even brighter than the brightest globular clusters. But this is not because they contain more stars. Instead, it is the result of the fact that their constituent stars are very much brighter than the stars constituting globular clusters. The most luminous stars in stellar associations are very young stars of spectral types 0 and O and B. They have absolute luminosities as bright as any star in the galaxy, on the order of 1 million times the luminosity of the Sun. Such stars have very short lifetimes, only lasting a few million years. With luminous stars of this type, there need not be very many to make up a highly luminous and conspicuous grouping. The total masses of stellar associations among to only a few hundred solar masses, with the population of stars being in the hundreds or in a few cases thousands. The size of stellar associations are large. The average diameter of those in the galaxy is about 250 light years. They are so large and loosely structured that their self-gravitation is insufficient to hold them together, and in a matter of a few million years the members disperse into surrounding space, becoming separate and unconnected stars in the galactic field. Let's now discuss moving groups. These objects are organizations of stars that share common measurable motions. Sometimes these do not form a noticeable clusters. This definition allows the term to be applied to a range of objects from the nearest gravitationally bound clusters to groups of widely spread stars with no apparent gravitational identity, which are discovered only by searching the catalogues of stars of common motion. Among the best known of the moving groups is the Hyades in the constellation Taurus, also known as the Taurus moving cluster or the Taurus stream. This system comprises the relatively dense Hyades cluster along with a few very distant members. It contains a total of about 350 stars, including several white dwarfs. Its center lies about 150 light-years away. Other notable moving stellar groups include the Ursa Major, Scorpius, Centaurus, the Pleiades groups. Besides these remote organizations, investigators have observed what appear to be groups of high-velocity stars near the Sun. One of these, called the Chrome Bridge 1830 group, consists of a number of subdwarfs and the star RR Lyrae, after which the RR Lyrae variables were named. Recent advances in the study of moving groups have had an impact on the investigation of the kinematic history of stars and on the absolute calibration of the distance scale of the galaxy. Moving groups have proved particularly useful with respect to the latter because their commonality of motion enables astronomers to determine accurately for the nearer examples the distance of each individual member together with nearby parallax stars. Moving group parallaxes provide the basis for the galactic distance scale. Astronomers have found the Hyades moving cluster well suited for their purpose. It is close enough to permit the reliable application of the method, and it has enough members of re- reducing an accurate age. One of the basic problems of using moving groups for distance determination is the selection of members. In the case of Hyades, this has been done very carefully but not without considerable dispute. The members of a moving group and its actual existence are established by the degree to which their motions define a common convergent point in the sky. One technique is to determine the coordinates of the poles of the great circles defined by the proper motions and positions of individual stars. The positions of the poles will define a great circle, and one of its poles will be the convergent point for the moving group. Membership of stars can be established by criteria applied to the distances of proper motion poles of individual stars from the mean great circle. The reliability of the existence